Alright, hi everybody. So today we're going to talk about Le Chatelier's principle. And you know this from last year, maybe you remember it, maybe not, but the idea is that once you're at equilibrium, what can we do or what would happen to the system if we were to stress it? And this is what Le Chatelier's principle talks about. It says, a system at equilibrium, once stressed, will um, react to that stress um, to reestablish equilibrium. Reestablish equilibrium. So what are the terms that we use? Well, we use the term stress, and the stress could be temperature, pressure, or concentration. And then we use the term shift. And what a shift means, if we shift to the left, this means that the reverse reaction is favored. It also means that we will increase the concentration of reactants while decreasing the concentration of products. If we shift to the right, it's all the opposite. The forward reaction is favored. You decrease the concentration of the reactants, and you increase the concentration of the products. And so these describe the shifts, and they describe the stresses. Let's get into the stresses. So the first one would be a temperature effect. And so you could do two things. You could either increase the temperature or decrease the temperature. If we increase the temperature, the first thing to note that's important to keep in mind is that when we increase the temperature, both the forward and reverse reactions increase. And that's something that the AP likes to trick you with and people don't really think about. But that's sort of what's going on. I mean, both the forward and the reverse reactions are increasing. Temperature always increases the rates. But what's happening here is that the endothermic reaction will increase more. And so you will favor the endothermic reaction. The exothermic reaction, it will increase less. And so the endothermic ends up being favored. If we decrease the temperature, then both the forward and reverse reactions decrease. But now the endo decreases more, and the exo decreases less. So temperature is really the only thing that affects K. You can only shift the equilibrium constant Kc or Kp by temperature changes. Now I can't tell you the K will increase or decrease. It depends on which way the reaction shifts if you have more products or reactants. If you shift to the right, you'll get an increase in K. You shift to the left, you'll get a decrease. But that's only true with temperature. What does a problem look like? Well, if you had something like A plus heat goes to B, if I increase the temperature, the endothermic reaction will be favored. And in this case, the endothermic reaction is going forward. So this is endo. So increasing temperature, this will result in an increase in B, a decrease in A, and a K that will go up. That's for this specific reaction. If you go in reverse, your exo, so decreasing temperature, will in fact lead to the exothermic reaction being favored. A will go up, B will go down, and K will go down as well. Now, maybe in class we can discuss why this actually happens. Why is the endo favored over the exo? It has to do with activation energy. And we can talk about that in class, but that would take a good 5 to 10 minutes to discuss that right here. And I want to keep this video where I get through all the stresses. All right, the next one is pressure. And so with pressure, if we, first of all, need to take into account that this is only for gaseous systems. Not everything needs to be a gas in the system, but there has to be at least one gas present. If you increase the pressure, which is a decrease in volume, this will cause a shift to the side with more, I'm sorry, that is less moles of gas. If you decrease pressure, which is increasing volume, you will shift to the side with more moles of gas. And this is actually something really interesting to think about. Why does this actually happen? And this, again, is something that's like pretty worthy an in-depth discussion in terms of, we could describe it in terms of K versus Q. We could describe it in terms of the mechanism with the rate law. And then we could also describe it in terms of collision theory. So we could get into all of that, and it would be interesting. The thing with pressure with gas is what you're really doing is you're changing concentration. So when we think about it in terms of how are we changing concentration, that's where we sort of need to take things into account. Okay, so I realized that my camera was into the screen here. So I don't know if you could see this. If you missed this first part right here where it says temperature effects, or this part right here, you shouldn't have missed anything, but I'll check the video just in case. Okay, so that's change in pressure. So if we have an example, like if we were to do N2 gas plus 3H2 gas yields 2NH3 gas, well, to count the moles on each side, we look at the coefficients. This has a 1 and a 3, that's 4 moles. On the right side, that's 2 moles. So if we were to increase the pressure, in this case, if we were to increase the pressure, then we would shift to the right. And what this would result in is this would result in a decrease in N2, decrease in H2, and an increase in NH3. If we decrease the pressure, well, then we would have the opposite shift occurring, and we would shift left. Now, the last type of stress that you could have is a change in concentration. So what occurs when we change the concentration? Well, depends on what we're changing. But if basically, in general terms, if we increase the concentration, we will shift away from the increase. So if we increase the reactant concentration, it will result in a decrease in reactants and an increase in products. Now, if we were to increase the products, that would result in an increase in reactants and a decrease in products. This first one over here, this is a shift to the right. This is a shift to the left. If we decrease concentration, then we shift toward the decrease. So if we decrease reactants, it will result in an increase in reactants, and it will result in a decrease of products. And we would shift to the left. If we decrease the products, then we would have an increase in products, a decrease in reactants, and we would shift to the right. So this seemed easy for people last year when they were doing this. And again, it's not meant to be that challenging for you. But, the idea is that you understand which way you actually shift and what's going on. One last stress or non-stress really is addition of a catalyst. With addition of a catalyst, there's no shift that occurs. Now what I wanted to spend a minute or two doing with you is just looking at this graphically, especially for concentration. If we look at concentration versus time, and we just have a simple system, A going to B. Well, if we take this and we look at it, if we have A, the reactant over time will decrease. And B, it may be higher than A or not, but I'm going to draw like this. Just fix that, sorry. So here's B. So let's say that we decide to stress out the system. Let's say that we decide that we're going to increase B. Well, if we increase the concentration of B, then we know that this should shift away from the increase. So this should result in an increase in A and a decrease in B. So let's do that on the graph here. So let's stress out the system by having an increase in A like this. Now we have this sudden increase in B. Like we said, A would increase. So the change looks like this. A increases slowly. B will decrease slowly from the increase, and then eventually you'll reach equilibrium again. Now notice what I say here, B decreases. But the idea is that B decreases from where you increased it to. It doesn't necessarily, or usually it does not, go below the initial concentration of B in purple. A increases slowly, and it will eventually level out and reach equilibrium too. Now look, the idea behind this is collision theory. If you increase B, there's more B to react. So that B will then react more. The reverse reaction will occur more frequently, and you will shift to the left. Now what if I were to do one more graph with you? This time we're going to do a decrease of one of them. So we'll do like this, and we'll do like this, and again we'll have A and B, and now we'll go ahead and we'll switch colors here, and we'll do a stress. So we have again A goes to B. Now let's do a decrease in B. So now we should shift towards B, and we should shift away from A. Well, if we lower B like this, to almost zero, let's go back a little bit. If we lower B like this, then B has decreased. It's going to react less with itself to form A. That means that A will start to form less and its concentration will go down. But here's where it gets weird. At first, A was not changed at all. A kept reacting to form B. So even though we decreased B, there was no initial effect on its creation rate. A was still reacting with itself and forming B. And so what ends up happening is you'll form some B back, and you'll get a rebound effect like this. Notice again how I draw B very carefully. I don't make it higher than it originally was. I think that's something that got lost on people last year. They're like, oh, B will increase. It'll increase from where you decreased it to, but it won't go back above its initial levels where it was in equilibrium. So tomorrow in class, we're going to practice some problems, but we're also going to talk about some of the reasons why the temperature and the pressure have the effects that they do. All right, thanks so much for watching and have a great day. That's it for equilibrium.